Okay, so this will help us decide what box we sit in, which obviously will help us to think about kind of more basically what is going on, what the physics is happening. For all of these things, just like we had to with a Reynolds number to figure out laminar versus turbulent, you have to look up where actually those boundaries are. So we have to look up so to figure out what is small, what is medium, what is large, you have to look that up. For flow, well, let me change how I'm wording that. For a flat plate, a vertical flat plate, Rayleigh number greater than about 10 to the 9 is needed for turbulent flow. And Rayleigh number less than about, I think it's 1300 is needed for conduction. So for that geometry, that's where those boundaries happen to lie, but that's something that you can't just know beforehand. So then there are obviously going to be, like we had different correlations for different Reynolds number. We can have different correlations for different flow regimes like this. So we can have a correlation for a different Rayleigh number. So one correlation, just to give a sense of kind of what's out there. Be something like the new salt number equal to 0.10 times the Rayleigh number to the 1/3. For a Rayleigh number of less than 10 to the 9. Or sorry, this is for not less than 10 to the 9. This is for greater than 10 to the 9 to like 10 to the 13. Okay, so it's going to be valid. It's a fit to data valid over the range that it kind of fits best. Another correlation so the new salt number is equal to 0.825 plus 0.387 times the Rayleigh number to the 1/6 divided by 1 plus 0.492 divided by the Prandtl number to the 9/16 with all of that bottom stuff raised to the 8/27 power. And then that whole thing is squared. Right. So I write that just to show, like, sometimes they can get kind of wacky. So this works pretty well for all values of Rayleigh number. So we can kind of go with maybe more basic ones that fit in specific cases. We can get uglier ones that are going to fit maybe more cases, but there's not a, like, we can get big and ugly and kind of goofy things. All of those, the powers and all of that stuff, those are fits to experimental data. There's not something like magical of fundamental physics that went into building that model, other than the fact that we knew the model had to be a function of Rayleigh number. And okay, maybe there's like a slight tweak because of Prandtl number, because that's going to be important too. So we kind of know what the fundamental quantities are that are going to go into the model. And then we take our data and we, shift and look at it until we get the prettiest fit to the experimental data that we have. And sometimes that ends up looking big and ugly and gross like that. So one of the things, whenever you're doing these kind of problems, you have to make sure that if you're using an empirical model, that it's an empirical model that is an accurate representation of whatever system that you happen to be looking at, and also have some idea of, some models work best in certain situations, other models might work best in other situations. Okay, so these are both for flow on a vertical plate. So I'm going to stop there with notes. So obviously, if you were to need to use any of these models, right, this is where you have to go and like filter through textbooks and try to figure out, what is my system? What does it actually look like? What correlations are going to be used for my system? Kind of what are the key dimensionless parameters? It's not going to be something that you're ever going to be able to like just know off the top of your head, unless it's something that you happen to be working with every day. So I want to spend the next little bit just showing us some simulation results. So we'll get some chance to play with this. It's kind of it's a super basic simulation software. At the same time, though, I think it's useful for just kind of quick visualization. You'll be able to see kind of where some problems arise maybe from some of the simulation results. I think this is supposed to be, I want these to be the same size. Those, okay. All right, so what we have here, two different plates. They're separated by an insulator so that like the results of one side are not dealing with the results of the other side. There are a couple thermometers on there. I don't know if you can read those, but you can see the white is 50 degrees. The blue background, like this whole background, is fluid. So I think actually I'm going to modify my simulation a little bit. No, I want to properties. Okay. All right, so we're going to see a little bit. We can move these. These are anemometers, so they can help us. How fast they spin is going to tell us something about how fast the fluid is flowing. So we'll put some anemometers next to each of these shapes. So before I run this simulation, right, we have these two different things. They're the same size. They're both at 50 degrees C. Before we run it, what is going to happen in the system? Like, which one is going to cool faster? And are we going to see temperature gradients? And what are those temperature gradients going to look like? Does anybody have any thoughts on that? Okay, so this is a simulation that we're going to be running. Let's go back to our system and look at, okay, so which is going to cool faster? That's going to be related to like how big convection is at the surface. So what is the Nusselt number? Let's look back. What is the Nusselt number generally? Right, it's generally going to be going up. Like all of our models, the Nusselt number is going to get bigger with the Rayleigh number, which is really the Grashof number. Okay, so Nusselt number should get bigger if the Grashof number gets bigger. So what matters for that? Okay, let's look back at our equation just for that. Right, I mean, that fits kind of with what we're talking about here. It's going to be a function of Grashof and Prandtl. So the Grashof number, what matters? So gravity is going to be the same in both cases. Beta, the thermal expansion, that's going to be the same in both cases because it's the same stuff. Same temperature difference, 50 degrees in both cases. Same fluid, so the viscosity is changing. So the only thing that's changing is L. Right, so we're going to have, right, the vertical dimension is going to be changing. So we're going to have way more convection on the, right, this is just for a vertical plate. So this tiny little dimension, there's going to be basically very small convection there and a lot on this surface here. What about like the bottom surface and the top surface here? Like the top surface of that plate and the bottom surface of that plate. Is convection going to be good in those cases? So again, let's look maybe at what we think the physics is going to be. So in those cases, let me pull up a few slides. Okay, so for a flat plate, we expect it to look something kind of like this. So it should be, this boundary layer should be growing from the bottom. Eventually it would turn turbulent. We can figure out exactly where that would be. For different kinds of plates, we're going to see different flow patterns. So they're all going to be buoyancy driven. So what we kind of expect to see for the horizontal plate, right, instead of like getting a nice flow up the whole side of it, right, we're going to kind of get, it's going to like come off, like as the fluid gets warm, that little pocket of fluid leaves and then another, so it's going to be kind of, right, a little bit like this guy here. And then the bottom surface of the plate is going to look a little bit like this guy here, where the fluid kind of gets, right, it can't rise because it's stuck underneath the plate. So it's going to kind of build up heat until it can escape around the sides. And once it escapes around the sides, then it'll pull new cold air into it. So just kind of thinking about how this goes, does anybody have predictions as to, I guess two things, which one is going to cool faster, or are they going to cool the same? And for the one on the right, I have two thermometers on it, one at the top and one kind of near the bottom. Which are those going to read the same value or different values? Which is going to be hotter and which is colder? Okay, predictions are, it's okay to be wrong. Okay, we'll make you talk since it's 8 a.m. or make you at least commit to something. So the one on the left is going to cool down faster. Raise your hand. The one on the left is going to cool down slower. Okay, pretty much everybody. The one on the right, so the top is going to be colder than the bottom. Bottom's going to stay hot longer. Raise your hand. The bottom is going to cool down faster. Raise your hand. All right, let's run it and find out. I'm going to stop it there. So we've gone just a tiny bit. You can see if I kind of zoom in, you can see this one on the left. The black outline is the actual shape. So you can see the heat getting kind of trapped underneath the shape because it can't rise anymore. It can't get out. So it has to go around the edges. It's kind of getting trapped, but the heat on the top, right, the top is staying really cool. So the top is actually cooling pretty quickly. What's happening, this one on the right side, you can see this, the boundary layer. This is the thermal boundary layer. You can see it growing from basically 0 at the bottom of the plate. You can see it growing as we're going up the plate, just like we kind of expected it to. We'll let it keep going. So you can see the little anemometers. This one is basically spinning continuously on the right-hand side. This one is kind of like hit or miss. Now we're at a point where on the left-hand side, the top of the plate is basically cold, and the bottom of the plate is the only thing that's really still hot. So if we stop it again there, our dark blue fluid is 0 degrees. So we are getting close to that. Down here at the bottom, we're at, you probably can't read it, but it's at 9.9 degrees, where the top is at 12.4. And this one on the left is still at like 18 degrees, 17.6. So we were all correct. And you can still see some of the same kinds of things where we have this nice growing boundary layer here on the right-hand side. So we're still getting better convection at the bottom, although things are starting to even out as our temperature differences are kind of driving things. But we're down here to like 6 and 7 degrees, and here we're still at 14. So we're having a really hard time cooling down here because all of that heat is getting trapped underneath our system. Okay, not that. This one. Okay, so this one, we have, again, kind of the same thing. I want to make that so that heat can flow out the top. Okay. So now we have a tilted, an angled thing. So we're going to see kind of a mix of effects where, right, it's not totally what the flat plate, what the horizontal plate was, but it's not totally vertical either. So we should see some of this, like the hot layer kind of peeling off. We should see some of that. And we should see some effects of like heat getting trapped on the underside. But again, it's going to be a little bit of a mix of the two of those. So we'll look at that. So you can see some of this heat peeling off the top. We're kind of seeing a lot of heat getting trapped underneath. Certainly different effects than what we see from kind of this nice flow that we can develop up both sides of the system. Can stop that. Okay. So we haven't looked at forced convection in a little bit, but here are two systems that we have looked at before. So in these two systems, we have a big fan here on the left-hand side, big fan on the left-hand side. Same kind of thing. We have 50 degrees C objects. In one, we have a flat plate. The other one, we have a sphere. So for both of these, we should expect the kind of the front end of the objects to cool down faster because that's where we're going to have our highest convection coefficients. So a lot of times that we've been doing calculations, we've been looking at average convection coefficients and kind of average temperatures, but we should see, right, we know for a flat plate, convection coefficient decreases as we go along the system. So we should see that by a really low temperature at the front edge and a somewhat higher temperature at the back edge. And we should see this nice boundary layer growth along the flat plate. The sphere is going to be a little bit weird because we should see the flow go over it, but then we should have some sort of wake kind of behind the object. So we'll look at what this one is. Yeah, so you can see already in this flat plate, the front end of it has cooled down a lot, where the back end is still essentially has not cooled at all. Right, if I drag this thermometer down here to the back, oh, my simulation stopped. If I drag my thermometer down to the back, let's reset. Okay, so we're cooling down, but much more slowly. And then you can see on this sphere up top, we actually get, this is kind of a fun pattern. You get like alternating vortexes. It's a very common pattern, actually. Sometimes you'll see it in even in rivers with like the river flowing around a rock. You'll see this alternating vortex pattern behind it. It's called a vortex street, which is kind of a fun name. But you see that a lot at fairly low Reynolds numbers. You can tell we're not, in both of these cases, you can see this nice boundary layer growth along the flat plate. But in both of these cases, you can tell we're not at really high speeds. We're not at really high Reynolds numbers. And this is where, right, we can do simulations like this. I can do it like live on my computer because we're at really low Reynolds numbers. If we try to, for example, increase our velocity to 0.2 meters per second, 0.2, which is like half a mile per hour. We'll see how that works. So if we try to run this simulation, so you can tell we're a lot faster here at the bottom. You can still see some of the same boundary layer growth. You can see we have a lot more turbulence in the flow. We'll stop that. We'll go up now to, from 0.2 meters per second, we'll say we want to go to 0.5 meters per second. You can tell the simulation, it's starting to look a little bit, there's board-like weirdness to it. It doesn't look like you maybe think that it actually should. Like there's occasionally, did you just see that weird thing happening down there? And if we tried to go to like 2 meters per second, at 2 meters per second, it just gives up. It says, stop it, that's too fast. I can't actually solve it. Basically, the differential equations exploded and it couldn't handle it. So one of the challenges with any simulation is basically as we start to increase turbulence, especially, our models can start to break down, even our computational models. So what happens actually, there's a lot of art that goes into making a good computational model. We're not going to go into this in this class, but there's a lot of art that goes into making good computational models, especially if they have turbulence. Okay, so okay, look at okay, so we talked kind of briefly about mixed convection. So again, we can kind of see that happening. Those two before were pretty purely forced convection, and you could just see that, like the top and the bottom surface were behaving the same. In this case, we'll have, you can see we have some boundary layer formation at the bottom and at the top, but also at the top, you get this effect of like the hot fluid kind of peeling off. So this would be a case where, I mean, visually you can see that it's operating in some kind of mixed, it's not purely one, it's not purely the other. But we have this would be a system where our Grashof number and Reynolds number are similar in size. Okay. Okay, so one of the key systems where we see free convection happening a lot is confined systems like this. Our book spends a fair bit of time talking about what these look like and how we can handle them. Again, we're going to have different models for these systems based on the same kinds of things, different correlations. But one of the things about free convection, probably even more so than other kinds of convection, is that the geometry matters a lot, like where gravity is. So this is, we have a kind of hot thing on the left side and a cold thing on the right side. We run this simulation. You can see it starts, it wanted to be conduction, right? If we set that up, like the initial heat transfer that's happening, it looks like it's conduction, but then that density difference takes over and we start to see the density difference starting to drive a flow. You can see if we give it a little bit of time, I have these set so that the two walls never change temperature. So they're stuck at 25 and 0. We can see eventually we'll get a nice kind of circular flow pattern emerging in the middle, where we see kind of the hot air going up and then the cold air coming and then it coming back down and heating up. And we get this nice circular current that forms between the two objects, which is going to obviously be able to fairly efficiently transfer heat between them. Okay. Same system, slightly different. I basically just moved the things closer. So in this case, right, you can see the heat transfer starts by conduction, but there's never big enough density differences to actually drive much of a flow at all. So it starts by conduction and then stays just conduction. So this would be a situation where, right, we can model this heat transfer and we can understand it without one of these recirculating currents. It would be a system where our Rayleigh number is small enough that we don't ever get this circular flow happening. So we can do that by changing either like viscosity or changing the spacing between the two plates or changing temperature difference. We can also derive a system like this by changing the geometry. I want to show you a little bit what I'm talking about with that. So if we drive Okay, if we flip the geometry, instead of having the left hand hot and the right hand cold, if we have the top hot and the bottom cold, again, now gravity is going to be kind of working in our favor, because the hot air is going to want to go up and the cold air is going to want to go down, which is exactly kind of where it starts. So if we run this situation, we never get density differences driving a flow because the density differences are in line with where the fluid is already. So we only ever get heat transfer by convection because there's kind of no place for the fluid to go. So we can drive, especially when we have confined things, which we can a lot in free convection. We have to really be careful with what's the geometry and what is actually happening in the fluid. Like, what are the dynamics? Is the fluid moving or is it stationary? Okay. Okay, and then of course, if we flipped it and we put the hot thing at the bottom, now our hot air is going to like peel off of that bottom surface very easily, and we're going to get a nice flow pattern emerging between the top and the bottom. So this, we get kind of a similar type of recirculating flow between that top and bottom surface. Okay. All right, we'll stop that one. Okay, last one. Okay, so last one. A lot of times this geometry actually shows up quite regularly, where you have a hot center and a cold outside, and there's like a fluid in between the two systems. So you have a fluid in this annulus. You can see in this as well, we start to see initially the heat transfer starts by conduction, but then the density differences take over, and that's going to drive, again, kind of a recirculating flow. This one is kind of cool because you get really like 4 areas of recirculation. So the heat kind of ends up going out the sides and then recirculating on the top and at the bottom of the channel. So you can see it kind of coming in this way and coming back down, as well as going like down and around at the bottom on all 4 corners. So for free convection, really setting up these kind of convection rolls, sometimes they're called, is going to be one of the kind of foundational like physics things that drives convection. And you really have to understand, like, what does the flow look like to make sure that you're thinking about it correctly, that you're modeling it correctly. And just to show a little bit the importance of the geometry in driving a whole variety of different types of flow. All right. Okay, again, just to show kind of briefly, I don't think you need to write any of these down, but just to show briefly that we're going to be kind of tailoring our models, right? People have done a whole bunch of experiments, fit their experiments to different equations, and then those are always going to have some certain bounds that they work in, and it's always going to be geometry dependent on top of like any other dependence or any other specific conditions that those things work in. So for example, if you wanted to model like a flat plate, like the thing that we did first. You have to model the top surface, the bottom surface, the edges. All of those things are going to behave differently. So you have to model them all differently because they're all different geometries, so different things are going to be happening at those surfaces. Okay. All right, so we'll wrap up today just with some kind of general thoughts, which is kind of what I've been talking about all day, but wrap up with some general thoughts on how to think about really not only convection, but building up empirical models of systems in general. So for new systems or systems that other people haven't done before, we can build we want to build empirical models and our engineering intuition really by two parts, by understanding the physics involved and through careful or targeted experiments. Right, so the kind of the worst thing that you can do when encountering a new system is just immediately jump in and start doing experiments to try to figure out, what things matter and how much they matter. You want to start before you dive into experiments and experimentation, or even building up a CAD model, like we showed. You want to first go to, okay, what's actually the physics involved? And can I look at maybe a pared down or simpler system to be able to just get at least like a rough idea of how things matter and how much they should matter, and what are the kind of the key parameters that I'm going to need to be keeping track of. For experimentation, that's super important, because if you can figure out from the physics that the things that really are going to matter are Prandtl number and, say, Grashof number, or Reynolds number and Prandtl number, or Rayleigh, or like whatever. We have all kinds of these different things. But if you can figure out what are the key things that are going to matter, then that immediately targets your experiments. And you say, I don't have to do 500 experiments. I can do like 4 and get a pretty good idea of how things are going to be changing and varying. Right. So for the physics, we're looking at right, things like conservation, of mass, F equals ma, conservation of energy, right, things like right, this, like U star, du star, dx star plus v star, du star, dy star. So the equation that we just wrote, 1 over Grashof to the 1/2 d squared dy star squared, right? So that's F equals MA. But the key thing to note for this is you don't have to like go it alone and start and do all of this, the heavy lifting by yourself. Other people have already done this. So your job is to kind of look at the results that other people have derived or come across for similar systems. And you're trying to figure out from the physics, like what are the important parameters? How does geometry affect it? What are the key dimensionless groups or the non-dimensional groups that we should be thinking about or we should be looking at? So you're looking at others' results, looking at like key dimensionless groups, flow patterns, laminar versus turbulent flow. How do you tell? How can you tell what flow regime you happen to be in? You're trying to get an understanding of kind of the basic physics that are at play, initially using kind of what other people have done for things that are, maybe they're not exactly the same, but at least like in the same realm of what's happening. So you have this goofy shaped object that you're trying to design. You can look at physics of flow over other objects and get a basic sense of what's important and how much and what do I need to think about from kind of a basic physics level. You're really looking at you can get a lot of intuition by looking at the solution to an easy, and I'll put easy in quotes, to an easy problem. And that's really where I think, right, that's why we've spent so much time dealing with some of these analytical solutions, because I think that's where you start to build intuition about what matters and how much and what effects am I going to be seeing and what do I need to take account of. So you can gain a lot of the intuition, right? If you're trying to design something, you need to be able to think about the problem in like a new and interesting way. And to do that, you have to have an intuition as to like, if I am going to be changing this, how is that going to be able to affect things? And you can't like run a new simulation or do new calculations every time, like as you're brainstorming, right? You have to be able to have a basic understanding before you can kind of go into the brainstorming process and start to figure out like what different designs or different approaches I'm going to be able to start to target, to then be able to do some more detailed analysis, whether that's more modeling like we've done in this class, or whether that's kind of a mix of some early modeling and then more advanced simulation, or whatever it is. At like the brainstorming level, you have to have an intuition, otherwise you're like hopelessly lost because you can't come up with good ideas because you don't know what a good idea, like what makes up a good idea. So that's where I think really looking at simple problems is super powerful to start to build up this intuition as to like what matters and how much and what we should be thinking about. Okay. Right. So just as like an example of that, right, I'm talking about something like nu salt equals 0.664 Reynolds to the 1/2, Prandtl to the 1/3. So this is obviously flow over a flat plate. So the reason we spend so much time on simple problems like that is because it can give us a feel and an intuition of how to think about things like this. And again, what matters and how much. Then the next step is kind of once you have this basic understanding, then you either move to experiments or simulation, and kind of targeted experiments, targeted simulation, because those are the things that take a lot more time, a lot more effort, a lot more resources from you to be able to like actually kind of implement or to be able to look at. It's 9:20. We'll pick this up kind of briefly next time. But hope you guys have a good last weekend before the weekend before exams, which is a little bit crazy. But we'll, yeah, look forward to see you back here on Tuesday.